Hello. So today we will be discussing a new topic. It is about work and energy. You had learned in your school days that any force can do some work. How did you define the work? You define the work as force times the displacement. But over here you should be very careful because the force, it may be constant or it may change. Okay, so things that you keep in mind, that you need to keep in mind. The force can be constant or it can change. For example, if I move this pen right here, okay, I cannot guarantee that I am supplying the same force throughout. Okay, so that is why the force, it can change. And also that you may notice is the force, okay, the object may not move in the same direction as the force. Okay, so these are the things that you really need to keep in mind. Okay, for example, okay, I am having this duster. You can see that I am tilting the pen a bit. Okay, I can even, okay, I can make it like this. Okay, if I am supplying a force even in that side, okay, like that. Okay, but I am making it slightly slanted. Okay, even if I apply a force like this, sometimes the object may move in this way. Okay, so you have to be very careful. Okay, so even though you are applying in this direction, the object is moving in this way. But one thing that you must remember, that because forces are vectors, they can always be resolved into that direction. Okay, so when calculating the work done, okay, you also need to be a bit careful about the direction of the force. Okay, for example, okay, let's see. Okay, if F is constant, if the force F is constant, then the work done, it's defined as Fd, where d is the distance. Okay, so over here what is happening, you are moving an object from here to here, and this distance is d. You are applying the same force throughout. Okay, and the object is moving along the direction of the force, so we will be defining as Fd. Okay, but over here, if F is in another direction, is acting at an angle theta, and still constant, and F is constant, then W, how much will it be? So what is happening over here? So you are having an object, but then you are applying a force in this way. Okay, the force that you are applying, okay, something like this, but it is still moving along this distance. So how will we calculate the work done over here? You can just take this angle theta, so resolve the force in this direction. It will be F cos theta d, okay, times the displacement d. So this is what is happening. Okay, this is the case when F is constant. But what if it is not constant? Okay, because the force may depend on the distance. Okay, for example, for this much of a distance, I am applying the same force. Again, I am moving it very slowly, and then I move it very fast. So it depends on the distance. For this much of distance, okay. Okay, so this is when integration comes into play. If F is not constant. Okay, so F is no longer a constant force. But what can we say? we can assume that the force is constant for a very small distance. Okay, we can assume that the force is constant. Okay, it doesn't change much. Okay, if I vary the distance only a bit, so I can assume that the force is constant for a small displacement dx. Okay, then the work done for this small displacement because it is assumed to be constant, so we can write it as f dx. Okay, so over here what is happening, you are applying a force, but you are considering only a very small distance, but still we need a very huge distance from here to here. Okay, so what can we do? We can divide this one into this whole distance into very small portions. Okay, divide it into very small portions, and we can assume that for each of those distances, for each of those small displacement, the forces are constant. So for over here we are having a constant force, for another small displacement we are having a constant force. So the work done, it will be the work done for this small displacement plus the work done for this small displacement plus the work done for this small displacement. You keep on adding. Okay, but we have to add infinitely many times. That is why, therefore, total work done W, it will be integration. If this initial distance is x1 and the final distance is x2, then we can write it as f dx. Okay, because if you remember that integration is just an infinite summation. Okay, we had done something like that. Okay, so this will be the total work done, and again you cannot take f outside of this integration because it may not be constant. Okay, only if it is constant then you can take it outside. Okay, so you have to be very careful. So this is about the work done by a force. Okay, there are also types of forces which are called as conservative forces. Okay, a force is conservative if the work done depends only on the initial and final point. And not on the path taken. Okay, so what is happening over here? You are having a point over here. Okay, you are having an object here, and you are having an object here. Okay, you are having this object at point A, and you want to move this object to point B by applying a force. Some of you, okay, if you have to do it, then you will just apply a force directly. Okay, some of you may even move in this way. Some of you may move in another way. Some of you may even move something like this. Okay, this object like this. But if the total work done is the same, okay, for all of the possible cases, then it will be called a conservative force. Okay, because it doesn't depend on the part. If the work done for this part is the same for the work done in this part, it's the same for the work done in this part, okay, then it will be called a conservative force. Okay, so I hope that is clear. Alright. So the force due to gravity, it is a conservative force because, okay, if you want to raise an object from this height to this height, you will have to supply the same force, okay, whether you do it directly or you do it in this way, okay, or you may take another path, okay, but the force done against gravity, it will be the same. Okay, so that is an example of a conservative force. Now what we will discuss now is about energy. Energy, I will just define it very simply as the capacity to do work. So if you remember that there are two types of energy, the kinetic energy and the potential energy. Energy due to motion, okay, and this one, energy due to position or configuration. Okay, so over here, just to remind you what is kinetic energy. If a person is moving, then he will have some kinetic energy, okay, because that is due to his motion. Whereas position, for example, okay, even if I drop this one, okay, if I drop a pen from this height, okay, I'll drop it, then it can displace some other things. That is because due to its position, okay, due to the height, okay, so that is called as potential energy. Okay, so it has some capacity to do work. Okay, so how do we measure the kinetic energy? Okay, kinetic energy, it is measured, okay, because the particle will be moving at a velocity v. So how do we measure it? It is measured by supplying a force to stop it. By this measured as the work done by the force necessary to stop it. Okay, so if a particle is moving in this way, if I want to, okay, with velocity v, if I want to measure how much energy does it have, okay, I will just apply a force in this direction, okay, so that it will come to rest. Okay, so the velocity will change from v to 0. Okay, so once the velocity becomes 0, then I will measure it. I will use that as the measurement for energy. Okay, so over here, how will we do it? So if a particle is moving with velocity v, okay, this velocity, again, it can change with distance or it can change with time. Okay, so the total force experienced by this particle, okay, after supplying it, it will be m, force equal mass into acceleration, d2x dt squared or d2s d2 squared. Okay, I will use s. Okay, but this one can be written as mv dv ds. Okay, hence work done by the opposing force to stop the particle it is equal to minus, okay, because it is an opposing force. Okay, so over here what is happening, okay, the particle is moving over here and the force, okay, it's in this direction, so it will be minus, okay, because we need to resolve it in the same direction, so that's why it will be minus. Okay, and over here will be the force mv dv ds. The displacement, again, it is ds. Okay, you can even write dx if it is linear. Okay, so I will write it like this. So the velocity changes from v to 0. The velocity changes from v to 0 because we need to stop it, to stop the particle. So over here will be minus m. You can take it outside because the mass is constant. dv, so you will be having v dv, v to 0. So on simplifying, you will be having mv square by 2, v to 0. So ultimately you will be having 1 by 2 mv squared. Hence this one is the kinetic energy, because we have said that the kinetic energy, it is measured as the work done by the force necessary to stop it. So maybe you can write hence K is equal to work done by the opposing force to stop the particle, which is this. Okay, so that's why this is how we get the formula for the kinetic energy, because it is measured as the work done. Okay, so this is about kinetic energy. We will do more about potential energy, but first let us discuss something about the, okay, let me see. Okay, the principle of energy. This one states, the principle of energy states that, okay, if a particle moves from one point to another, on a smooth curve, under the action of conservative forces, then the change in kinetic energy is equal to the work done by the forces. Okay, so let us see what is happening here. So you are having so many forces in a plane. Okay, you are having so many forces in a plane, so that's why we'll be having two directions, x and y. These forces are making the particle to move from, okay, from maybe from one point A to another point B. Okay, so let us see. Okay, so it's moving from A to B. But because these forces, okay, they are acting over here. If you remember, we had done that forces can be combined into one single force, or sometimes they may even form a couple. Okay, so we will take that the forces can be combined. Okay, so what is happening? Ultimately, we will get only a single force. After combining all the forces, we will get only a single force. The force, it may not be constant. Okay, but since we are having a single force, okay, maybe I can even write it like this: solution. Okay, maybe as proof, let Fx equal total force. Okay, the forces can be resolved along the x-axis, so let the total force along x. Okay, and Fy equal total force along Oy. Okay, so Fx is acting in this direction and Fy, it is acting in this direction. Okay, it is the total force. Over here, what will we use? We will use tangential and normal directions. Okay, since we are using tangential and normal directions, okay, so this is the tangential direction. It is making an angle psi, and this one, it is the normal direction. Okay, so resolving the forces, resolving these forces now tangentially and normally. And normally we get, okay, Okay, so what will be the force along this direction? It will be mv dv ds. How did I get this one? Because this one, it is the acceleration, it is the tangential acceleration. Okay, let me just note it down. Tangential acceleration, it's v dv ds. Okay, so over here we need to resolve fx along this direction, so it will be fx cos psi. Okay, because we need to resolve it along this tangential direction, plus fy sine psi. If you resolve this one in this way, it will be fy sine psi. Okay, so this one is along the tangent. But if you notice, cos psi, okay, over here it is a tangent. Okay, this one is tangent, so it can have a very small length. Okay, let us consider a very small length ds. So this angle will still be psi. Okay, this corresponding horizontal distance, it will be dx. Okay, so we'll be having something like this. Okay, let me just expand this figure, even though it's very small. Okay, it's happening at this point. Okay, if I expand it, we'll be having something like this. Psi, over here it is ds, dx, dy. Okay, so this angle is psi, dx, dy. So cos psi fx cos psi. So cos psi will be cos psi will be ds dx ds plus fy dy ds. Sin psi, it will be this. Okay, so we will be having mv dv equal fx dx plus fy dy. Okay, so this is what is happening right now. Okay, let us just name this one as equation 1. Okay, now let us just analyze what this equation 1 is doing. Okay, in particular the right side. The right side, this is the force along x. This one is a very small displacement along x. So this one will be the work done along the x-axis. This one will be the work done along the y-axis for a very small distance. Okay. Okay, let me just write it down. The right hand side of 1 gives the sum of the work done along x and along O1 for a very small displacement. Okay, so this is what is happening. Okay, but we need to integrate this one. Okay, so the force depends on the angle, right? The force depends on the angle. So what I'm saying, I should also say that the angle depends on the force. Okay. What is making this particle to move? The thing that is making this particle to move, it is they are the forces. Okay. So the particle was over here. So over here we will be having another tangential angle, psi 1, psi 2. Okay. This psi 1 and psi 2 depends on the forces. Okay. So we can even say that fx, it is related to psi 1. Fy, it's related to psi. Okay. So the forces are all depending on psi. So what can happen? What can happen is sometimes, okay, if fx dx and fy dy are it's a complete differential of phi phi xy, then we can write this. Then we can write this whole thing as d phi. Okay, this one it will be equal to d phi. Okay, for a very small distance. What will happen over here? Okay, phi xy it's okay. Let me just give you an example about this. Okay, sometimes what is happening over here, the force, okay, it can depend on the distance as well. Okay, the force can depend on the distance. The force can depend on the distance. Suppose fx, okay, it depends on the distance. Suppose it is equal to y. Okay, let us just take this very example. Sometimes fy it's equal to x. Okay, just as an example. Okay, they may change. Then equation 1, it can be written as y dx plus x dy. Right? But this one can be combined as dxy. dxy will be x dy plus y dx. Okay, so sometimes this may happen. This is what I have written over here. If fx is a complete differential. By complete, it means that we can write something like this. It will be exact. Okay, it will be an exact differential. We can write it as dxy. So over here, phi xy is equal to xy, just as an example. Okay, so sometimes it may happen like this. Okay, where okay, so if it happens, then we can write it like this. Okay, as d phi only. Okay, just like I had given example. So we can just integrate this one. So we will be having this one as half mv squared equal phi xy phi plus c. Okay, but phi depends on the values of x and y. So that's why sometimes we can even write phi xy plus c. Okay, but if you notice again, phi xy, it is the right hand side. It is the right hand side after integrating. Okay, so it will be the work done. Okay, so that is why this phi xy, it will be called as the work function. Okay. Okay, initially, okay, the particle is at x naught y naught with velocity u, then okay, so the particle is at x naught y naught with velocity u, so we can substitute over here, then half mu squared equal 5 x naught y naught plus c. Substituted here, substituting in equation A, we will be having, substituting in A, we will be having half mv squared equal 5xy plus c, which is half mu squared minus 5x naught y naught. Okay, so half mv squared minus half mu squared equal 5xy minus 5x naught y naught. So this is what is happening. Okay, this left hand side, it is the change in kinetic energy, and this right hand side, it is the work done. Okay, it is the work done on moving the particle from x naught y naught to a new position x y. Okay, because just like I had said, the right hand side, it is the work done. Okay, after integrating. Hence, kinetic energy change in K equal work done. Okay, note, as a note, phi xy, it's called as the work function. Fx dx phi xy is called as the work function. Of the system. Okay, so this is a very important theorem. We will be using this one to solve some exercises later on. You just need to remember that the change in kinetic energy is equal to the work done. Until next time.